Hello, this is a continuation of our class meeting that we had on Wednesday, but because of the other things that we talked about as far as academic integrity and technology issues, we didn't really get into the meat of the materials for the week. So I'm going to be talking about those now, and hopefully you can all hear me. It's kind of strange because I'm doing this on my own. There's no one here really to interact with. So I'm going to just kind of pick up where I left off, and if you do have any questions, feel free to email me or post them on the discussion board. We left off talking about the week 3 assignment, and I did mention this in our class session, that you have some exercises due this week, and these exercises are in your textbook, exercise 5.5 and 5.14. Again, I'm going to ask that you submit them as a Word document through the Blackboard submission process. Make sure you label each answer with the exercise number. I do want a Word document. Don't send me a PDF or some other format. A Word document gives me the ability to insert comments and so forth right in your document and get that back to you so that you have feedback. What I want you to do when you're doing your assignment this week, and this is important, I want you to explain your answers. It's possible for some of the exercises this week, you could give me a very simple, one word or one sentence answer. That's not what I'm looking for. If your answer is, something like shortest job first scheduling, for example, I want you to explain to me why you think that's the answer. What calculations did you do? What did you look at that made you think that that was the answer to the question? So you have to explain your answers, not just give me a short phrase or one-word answer. And again, I think we've kind of talked about this maybe more than you would have liked to, but all your answers should be your original work. Okay? So no one's here to ask me questions, so I'll just continue on. But if you do have any questions, feel free to send them to me or post them on the discussion board. This week's topics basically have to do with scheduling the CPU. We're going to be looking at different CPU scheduling algorithms. We're going to be looking at how you would evaluate CPU scheduling algorithms and look at the scheduling algorithms of different operating systems. Of course, I won't be going through all this in the slides, but again, this is all in your textbook. So when we talk about CPU scheduling, the goal here is to keep the CPU busy. Remember that in a multi-programming system, one of the things that we're doing is we're having multiple jobs or programs or processes in memory at one time, and then we're doing a context switch. We're switching between the different processes in order to keep the CPU busy, because a lot of times a process on a system will be waiting for I/O, waiting for the user to enter a value. There's a number of reasons why the CPU would be idle, okay? The program is waiting for something. The I/O, or waiting for I/O, is the main reason it might be idle. There are other reasons that it could be idle, that it could not be doing anything. For instance, there may not be any processes that are ready to be executed, and then the CPU would be idle. But mostly, a lot of time is spent waiting for I/O to happen, because of course it's a lot slower for things to be read from disk or come in from a keyboard than it is to access things in memory. The short-term scheduler is responsible for allocating the CPU to the process that is ready. Okay, so if it's ready to run, it's given the CPU. The CPU is a resource just like memory and disk and the other resources on our computer. So we talk about allocating the CPU to a process, which simply means that that process can be run on the CPU. The dispatcher is what gives control of the CPU to the selected process. So it's really the dispatcher that often does the context switch. We'll switch between kernel mode and user mode and go to the proper location in the user program to restart the program. Okay, and you kind of looked at that when we looked at doing context switches and the different modes that we talked about in the last chapters. There's something that your book calls dispatch latency, and that's the time it takes for the dispatcher to stop one process and start another. And this is something important to look at when you're creating an operating system, because if you're switching processes in order for the CPU to stay busy, you don't want that to take a lot of time. Because if a program is very CPU bound, okay, and it's doing a lot of calculations or whatever, and then it hits a wait for I/O, you're going to want to make sure that it doesn't take so much time to do the switch to another process that it outweighs the gain you would have by switching to another process. Do you see what I'm saying? Basically, you want to make sure that you can do these switches very quickly, because otherwise the other processes are just waiting for something to happen, and what's really happening is it's just trying to switch between processes. So typically when you look at a program, it's going to be a series of CPU and I/O burst cycles, and simply what that means is that the process is alternating between using the CPU and waiting for I/O. So CPU-bound programs have fewer, longer CPU bursts, and I/O-bound programs have more frequent, shorter CPU bursts, because a lot of its time is being spent waiting for I/O. So assume that a process is currently executing. When would the short-term scheduler need to select the next process from the ready queue? Okay, we talked about processes being in different states, being ready, being waiting, waiting for I/O, going from running to ready state, different things that are happening in the CPU. I want you to just take a minute and think about when would you need to select the next process, or when would the scheduler need to select the next process from the ready queue? When is it doing this decision, making this scheduling decision? So no one's here to answer that question, so I'm just going to be quiet for a moment and let you think about that and come up with your own answer, and then I'll move on. Okay, basically we're looking at a number of different cases where the CPU scheduler would have to be invoked to switch processes. When a process goes from a running state to a waiting state, it can give up the CPU. So that's one of the times when the scheduler would run. When a process is waiting for I/O or waiting for a child process to terminate, that's one case where the scheduler would schedule a new process. Another time the scheduler would schedule a new process is when a process terminates. Okay, the process is over, it exits the system. That would be another case when the scheduler would have to choose a new process to run. The third case would be when the process switches from a running state to a ready state. And if you remember from when we talked about the states, this would happen when an interrupt occurs. The process was already running. It's not waiting for anything, but an interrupt happens, so the system has to handle the interrupt so that the process that was running will be switched out of memory, a new process will be switched in to handle the interrupt, and then another process will be scheduled after the interrupt is handled. So when a process switches from the running state to the ready state due to an interrupt, the scheduler will be invoked. And then finally, when a process switches from the waiting state to the ready state, in other words, maybe it was waiting for I/O, and now the I/O processor has signaled that it's done doing whatever I/O it had to do, that process now is ready because its I/O has completed, and it could be allocated the CPU again. So there are 4 different cases in which the scheduler would be invoked, and we can break them down by what is called cooperative scheduling and what is called preemptive scheduling. In the cooperative scheduling case, this is when the process that had been running, that had been allocated the CPU, is either going to need to wait for something or is done, then another process can be scheduled. So this is cooperative. The process that was running gets to run until it can't do anything anymore, and then another process will be scheduled. The other kind of scheduling is called preemptive scheduling. And preemptive scheduling, it happens on systems where you have a hardware interrupt. Okay, it's something where your process was running and it could continue running, but it got interrupted. Okay, so the interrupt happens, the process that was currently allocated to CPU gets forced out of memory in this case. So it's more of a preemptive scheduling rather than cooperative. Cooperative scheduling was used in older operating systems because there was no support for interrupts in the hardware. So there wasn't this kind of preemptive hardware interrupt that would force the process to stop running. In the newer operating systems, newer hardware, we have hardware interrupts, and we also have things where we're preventing a process from hogging the CPU. Okay, we're getting it out of memory if it's hogging the CPU for too long. Okay, so that's just 2 kinds of scheduling and some of the different cases in which the scheduler would be invoked. So if we look at some scheduling criteria, how do we measure how well the scheduler is doing? What kinds of things need to be considered? Well, one thing is the CPU utilization. We want the scheduler to keep the CPU as busy as possible. But there's more than that when you're scheduling. There's other trade-offs that need to be made. Another thing that we look at is throughput. Throughput is the number of processes that complete their execution during a certain period of time. Okay, so we're looking at how quickly things are getting through the system. Turnaround time, okay? This is measuring the time spent waiting, getting into memory, waiting in the ready queue, executing on the CPU, doing I/O, everything from the time the process is submitted, comes into the system until it's completed. That whole thing is called turnaround time. Okay, another thing to consider is waiting time. Waiting time is the sum of the amount of time a process has been waiting in the ready queue. Okay, so we want to keep track of that. We don't want certain processes to be starved. They're just in the ready queue for a long, in the waiting queue rather, for a long, long time. And we want to make sure that if they're ready, they are getting allocated the CPU at some point. And then we also want to look at response time, especially if we're working in an interactive system. The response time is the amount of time from when a request was made until the first response is produced. So here, if we're in an interactive system, you type in something on your computer or you click something with your mouse, response time counts the amount of time from when that event occurred, that click, or you hit enter, when that occurred, until the system starts outputting the response to you. It doesn't count the time of the outputting of the response, because that's actually a part of the I/O, but it's how long before the system actually has some results to give back to you. It starts responding to whatever your request was. So we have all this different criteria that the scheduler could use. And I want you to think about for a minute, what is the most important? Which of these would you maximize? In other words, which of these would you want to be a big number? And which of these would you minimize? Which would you want to be very small? And is there something here that's very important? So if we look at that scheduling criteria, utilization, waiting time, throughput, response time, and turnaround time, which should be maximized? In other words, what do you want to have the biggest numbers? Well, I would say that the two things you want to maximize would be the CPU utilization. You want the CPU to be utilized as much as it possibly can, and also the throughput. You want as many processes, as many jobs to get through the system as possibly can. So those two things you want to maximize. You want to minimize the waiting time, the response time, and the turnaround time. You want these to be as small as they possibly can. Okay, you don't want things waiting in the ready queue for a long period of time. You want them to be allocated the CPU as soon as possible. You want your response time to be very small, because you want the users to be getting that interactive feedback back from the system very quickly. And then the turnaround time, of course, you want that to be very small as well. In other words, how long does it take for, something to get into the system and complete in the system? You want that to be very short as you could possibly make it. So there are some things we want to maximize, some things we want to minimize. And as far as what's the most important, well, this is kind of a trick question, because the answer is it depends. It depends on your system. What is this system being used for? In an interactive system, the response time might be the most important measurement that you can take to see if the system is meeting the needs of the users. Okay? If you have a batch system, it might be that the throughput or the turnaround time is the most important. Okay? So there's not one answer to which is the most important. The answer is it depends, and then you look at the users and the use of your system and decide how to tune it to maximize and minimize certain things. All right? So if you have any questions at this point, feel free to email me, but I'm going to continue on. Okay, your book talks about first come, first served scheduling. And this is very similar to what you would see if you use a FIFO queue to implement your scheduler. In other words, the first thing that comes into the queue is the first thing that gets allocated the CPU. And so we can look at this and say, okay, if we have three processes, P1, P2, and P3, and the CPU burst for each of these is 24, 3, and 3, respectively, we can say what's going to happen is at time 0, process 1 would come into the system, It's the first one to request the CPU, so it would be allocated the CPU. Process 2 and Process 3, even though they may come into the system immediately after Process 1, Process 2 is going to wait at least 24 milliseconds for Process 1 to complete. Okay, so Process 2 isn't going to start until 24 seconds after Process 1 started. Process 3, if it arrived after Process 2, it's going to have to wait for Process 1 and Process 2 to complete before it is allocated the CPU. So each process waits in the queue until the CPU becomes available. So the prior process has finished, or it goes to something where it's waiting for I/O. But in this case, we'll just look at, we're just looking at the CPU burst. Okay, so for whatever reason, the process is done with the CPU and the next process can be scheduled. So the average wait time is really the average time of how long process 1 waited, plus the average time, or the amount of time process 2 waited, and then the amount of time process 3 waited, and then we divide that by 3. So the average waiting time would be 0 seconds for process 1, plus 24 seconds for process 2, plus 27 seconds for process 3, which, if we add that up and divide by 3, would give us an average of 17. Okay, so 17 milliseconds was the average. Now, obviously, the order is going to significantly affect the average wait time, because if process 2 entered the system first, it would be scheduled immediately. The next process would only be waiting 3 seconds, and if the next process happened to be process 3, then process 1, if that was the third process that came into the system, it would only be waiting 6 seconds. So we'd have 0, 3, and 6, which adds up to 9, and the average wait time would be 3 seconds. You see, so the order here is going to be very important when we're using the first come, first served scheduling. And we don't always have control over the order of when these processes arrive. Okay, so that's something important to realize for the first come, first served scheduling. And first come, first served scheduling is sometimes abbreviated as FCFS, first come, first served. Another scheduling algorithm that your book talks you through is the shortest job first algorithm. And here, the process that requests the CPU, this is wrong. This shouldn't say that requested first is allocated the CPU first. In this case, it's the process with the shortest amount of time. Let me just cross this out. Let me grab a pencil here. This is wrong. Cross that out. Okay, that is wrong. Sorry about that. It's actually with the shortest job first, what you want to do is look at what processes are waiting and choose the one that has the shortest CPU burst. So here, let's say that process 1 is going to have a 6-second CPU burst, process 2 is going to have an 8-second CPU burst, process 3 has a 3-second, and process 4 has a 3-second. Okay, we'd want to select process 4 to run first because it has the shortest burst of CPU time. So that's why here we see them running as process 4 followed by process 1 followed by process 3 followed by process 2, because we're going to run them from the shortest job to the longest job. Okay, and that's how we would want the CPU to schedule them. Okay, so ignore what it says on the top of the slide, and I'll fix that before I send the slides out to you. But what you want to do is, schedule the jobs according to how much how big their CPU bursts are going to be. Now that's kind of a problem. How do you know how long it's going to be? Okay, these are just things executing. They may have loops in them. They may have, lots of different characteristics that are going to make them have either short CPU bursts or long CPU bursts. In a batch system where, the jobs are all kind of running, not with any interaction and that type of thing, in that type of system, the person who submits the job can often assign the limit to that job and say, okay, this job isn't going to use any more than this much of the CPU. And so if everybody puts those limits on their jobs, then the scheduler could go through and choose which job depending on the estimated time limit for that job. But usually what's done is the next burst is predicted using the exponential average of the measured lengths of the previous bursts for the process. And your book goes into, all the detail for how the exponential average is calculated. And I'm going to kind of walk through that with you because I'd like to make sure that you understand. I changed the letters that are being used. It was using Greek letters in your textbook. That's very hard for me to enter on a slide, so I just changed them, but they have the same meaning. So Pn plus 1 is the predicted value of the next CPU burst. We're trying to figure out how long we think each process is going to run. There's a waiting factor, which is between 0 and 1. There's a time, which is the most recent CPU burst time, and then there's the previous prediction. Again, we have these processes coming in a series, one after the other, and we're trying to predict what's the prediction for the next burst. Okay, so we're going to assume that A is 1/2. Now A is the waiting factor between 0 and 1, and A of 1/2 means that the recent history and the past history are equally weighted. Okay, so A is used here in the formula, here and here, and what it's doing is actually kind of assigning the weight to, what's more important, the recent history or all of the past history of the different processes that have come in to the CPU. Okay, so we're going to look at that. P0 is 10. The first prediction is 10. Okay, just kind of pick that number. I predict the first CPU burst is going to be 10. Okay, so these kind of things are kind of set at the beginning before the system starts. We're saying, how are we going to weigh the history and what do we predict for the first burst? And we predict here that it's going to be 10. Then let's assume that the first CPU burst actually happened. Okay, the first process got into memory, was allocated the CPU, and the amount of time it took was 6. We can use this information now to predict the next burst, the burst for the next process, P1. Okay, so we're doing a couple things ahead of time, saying, okay, what do we, let's just guess how long the first process is going to run, the first burst is going to be, and let's assume that we're going to weigh our past history and our recent history equally by making A equal 1/2. All right, and then when the first burst happens and it's 6, now we have to adjust our prediction for the next process. Okay, and that's what we're going to do here. So again, this was the formula, and now I'm making my prediction for P1. So I predict, I know the first process that came into the system was at time 0, and that was 6 seconds. So for Pn plus 1, which is P1, I predict that next CPU burst is going to be 1/2, which is my A, times 6, which is the actual time that the first process ran. And then I'm going to add to that 1 minus 1/2, and this is where I'm weighing my previous history. And what was my previous prediction? It was 10. Okay, remember I said we're just going to guess P0 as 10? So now I do that calculation, and I get P1 equals 3 plus 1/2 times 10, which is equal to 3 plus 5. So I predict that my next CPU burst is going to be 8. Now let's assume that the next CPU burst happens, and that actual time that the CPU was used is 4. Okay, I'm now going to use what I know to predict the next CPU burst. So what do I predict that the third process is going to use on the CPU? So now I'm going to predict P2, and the way I do that is, again, I use this same formula. So P2 is equal to 1/2 times the time it was for T sub n, which in this case was 4. I'm going to add to that 1 minus A, which is still 1/2, and multiply that by P sub n. Okay, and P sub n was my prediction for the burst that just happened. So now I get P sub 2 is 1/2 times what I had as my actual time plus 1 minus my prediction, which is equal to 2 plus 4, which gives me 6. Okay, 6 is my prediction for the next CPU burst. Let's assume that it happens and it's 6. Great, I know I'm on the right track. My CPU prediction matched my CPU actual burst time. So see, I keep refining this algorithm as these processes are going through the system. I'm refining this estimate because I said equally weigh my previous estimates, my past history and my recent history. So now, when I go to predict the next CPU burst, now I say it's 1/2 times 6 plus 1/2 times 6, which gives me 3 plus 3, which is 6. So I predict that my next CPU burst is going to be 6. Now this time, the CPU burst happens and it's only 4. I go through the calculation again, and here when I say I mean I'm the scheduler. I go through the calculation again, and now I think that the next CPU burst is going to be 5, and so on. Okay, so you could see how I'm kind of predicting what's going to happen based on the CPU bursts that actually do happen. All right, so you can kind of step through this. It does step through it in your book, but it's important to understand, you know, how that's actually being calculated. And your book has a nice little graph that shows you, you know, different processes and different bursts as they happen, and then, you know, how you can predict for that process what the next burst will be. Okay, so remember here we're talking about a process that has, you know, different CPU bursts because it's not going to always have the same size CPU bursts. And so how do we predict each time this process runs how big its next CPU burst is going to be? And that's what this whole calculation does, is it looks at the bursts as they come in, as they happen, and uses that history to help predict what's going to happen next. Okay, so it's really helpful, I think, if you kind of walk through this and step through this on your own to understand really what the scheduler is doing. All right, so you're going to be kind of looking at that. Again, I'm not going to pause here for questions because you're not here to ask me any, but email me if you have a question on exponential averaging. But we're going to kind of look at this when we do our first exercise. This says, consider the exponential average formula used to predict the length of the next CPU burst. What are the implications of assigning the following values to the parameters used by the algorithm? So again, here it's using the Greek letters where I changed them to things I could type easily on my slide. But here you have to assume that the A is 0 and the estimate is 100 milliseconds. And here you estimate that it's 0.99 and 10 milliseconds. Okay, so what's going to happen, what will these estimates kind of look like if you assume those values? Okay, so that's what you have to think about. Kind of think about what is, what's it going to be predicting under these conditions? Okay, so you're really looking at, what? How can I explain this? When the alpha is 0 and it's 100 milliseconds was the prediction, what's going to happen? What will the predictions look like for the next CPU burst? When alpha is 0.99 and we have a value of 10 milliseconds, what's going to happen? How are we weighing things when alpha is 0.99? How are we weighing it? What is it looking at, and what is it giving more weight to as it's predicting what's going to happen next? Okay? So you want to kind of look at that formula and play around with the numbers a little bit, and then tell me, what, given these values, because, we went through an example with, 1/2 and starting at 10 milliseconds, what was going to happen, what happens in these cases? All right, so I want you to take a look at that and give me your answer and your explanation. Okay, I want you to explain why you think whatever's going to happen is going to happen. All right, so that's one of your homework assignments for this week. Alrighty. Another scheduling algorithm that your book goes through is the preemptive shortest job first. Okay, we talked a little bit about shortest job first and what that meant. Now we're looking at another scheduling algorithm that says if the CPU burst of a new process is less than the time remaining in the current burst, the new process is allocated the CPU. Okay, so here we look at these processes. They arrive at certain times and they have a certain burst time. So here's what happens. P1 starts executing. It only executes one unit before P2 enters the system. Well, P2 only has a burst time of 4, which was shorter than what process 1 has left. Process 1 is an 8 millisecond time. So process 1 executed 1 second, still has 7 seconds left when process 2 enters and only has a 4-second wait. Okay? So process 2 is going to get to execute its whole time, even though process 3 and process 4 enter the system. Because when process 3 enters, its burst time is 9, which is greater than the 4 seconds that process 2 had, and process 4 has a burst time of 5, which is also greater than the 4-second time that process 2 had. So process 2 is going to be allowed to continue executing. Once it finishes, the next shortest job is going to be process 4, and then when it finishes, the next shortest job is going to be process 1, because remember it only had 7 seconds left, and then finally process 3. So that's the preemptive job scheduling, or preemptive shortest job first scheduling. And so you can just kind of see how the next process to be allocated the CPU really depended on how much time it was going to use the CPU, and the shortest job got the CPU. So we could calculate the average time for the preemptive shortest job first, and we would get 6.5 milliseconds. If we calculate the cooperative shortest job first, remember we said there's cooperative and there's preemptive scheduling. Cooperative says, you know, wait till one thing is done before you schedule the next thing. Then we would have a 7.75 time if we scheduled it shortest job first. Okay, so all these different trade-offs and decisions are made, and it's going to affect your throughput, your response time, how much your processes are waiting, and so forth, and that's the job of the scheduler. So there's all these options that you have if you're writing a scheduler or if you're setting up a scheduler as to how you want that scheduler to work. Okay, then there's something called priority scheduling. And priority scheduling, a priority is assigned to a process. And the priority could be a calculated value that's calculated based on, you know, time limits, memory requirements, the I/O to CPU burst ratio, or any other metrics, you know, any other things that you know about this process. And we could give it a priority based on that. Or it could be based on external factors. In other words, how important is this process to whatever your system is supposed to be doing? How much are they paying to use the system? Some systems, you know, you pay for how much time you use it, and maybe if you pay, you know, $5 an hour, you have a very low priority, and somebody who's willing to pay $100 an hour has a much higher priority. Okay, and the system can be set up that way. It could be based on, you know, who's sponsoring the work, what department is sponsoring, you know, this process that's being run. In other words, maybe the payroll department has a lower priority than the factory automation, because you want the factory automation to be using the CPU more than, you know, the thing, you know, doing the accounting and doing your general ledger. Okay, so that might be the way the priority is set. Priority can also be preemptive or cooperative, and that just means that with preemptive, the CPU will be allocated to a new process if the new process has a higher priority, and it's cooperative if the new process, if it has a higher priority, it doesn't preempt what's in the CPU, but simply goes to the front of the queue. It kind of goes to the front of the line if it has a high priority. All right, so there's a whole you know, way that you're going to be putting things in the queue depending on their priority, and then whether or not they actually preempt the process that has the CPU is a whole other issue. So there's two kinds of scheduling again. The thing you have to worry about with priority scheduling is blocking. Okay, if high priority jobs keep coming into the system and they keep getting the CPU before low priority jobs, the low priority jobs could wait forever. So what you do in a system is you do something called aging. And with aging, you gradually increase a process's priority as it's waiting. So if something has to wait and it's waiting and it's waiting and it's waiting, you might bump the priority of that process up a little bit. And then if it's still waiting and doesn't get the CPU, you bump it up higher and higher and higher, and eventually it's going to be the highest priority job in the system and it will get the CPU. Okay, so that's one thing that you can do with priority scheduling so that a process doesn't get starved and never get the CPU. And again, your book goes through examples of priority scheduling, where here we have, different processes that enter the system. They have different burst times, but they're scheduled according to their priority. So here, process 2 has the highest priority. Let's assume that the lower numbers mean that it's a higher priority process. So process 2 gets scheduled first, then process 5, then process 1, then process 3, and then process 4. So they're just scheduled according to their priorities, and in this case, the average wait time for the processes would be 8.2 seconds, or milliseconds rather, 8.2 milliseconds. Note, however, that the priorities might change over time. Remember that I said that we may be doing something where we have preemptive scheduling and we don't want things to be starved, so we're increasing or possibly even decreasing priorities to make sure that certain processes do get a chance at being allocated the CPU. Okay, another type of scheduling that you'll see, and this is usually done with interactive systems, and this is a round-robin scheduling. So in a round-robin scheduling system, and this is often abbreviated RR, you define a time quantum or a time slice, and the processes never have the CPU for more than one quantum, more than one time slice. So the scheduler is going to be scheduling when the current process relinquishes the CPU in less than one quantum, or the one quantum passes and a timer interrupt occurs. So we're keeping track of how long, and we talked about this in one of the earlier chapters, we're keeping track of how long a process has the CPU. So the scheduler now is scheduling something every time period, every time slice or quantum, and it could be scheduling because a process gave up the CPU when it was done, or the time passes, so an interrupt occurred, and a new process will get into memory. In either case, the process gives up the CPU and is moved to the end of the queue, and then the process at the front of the queue is allocated the CPU. So here we're just going through the queue and in allocating the CPU to a process one at a time. If the process either gives up the CPU or uses up its whole time slice, it just gets moved to the end of the line and the next process runs. Okay? Here you have to be careful that the quantum, the time slice that you're using is larger than the context switch time. Remember we talked about this latency and what it takes to actually switch between processes. And you want to be careful too not to make it too large, because then you'll just end up with a first come first serve system scheduling. Okay, that should be first come, first serve. That's a typo again. I'll fix that too. Let's see if I can write here. First come, first. It's hard to write with my mouse. First serve. All right, there we go. All right, so it's first come, first serve if the quantum is too large. All right. Oops. So I'll fix that before I send you these slides. Excuse me, I'm getting a little hoarse here. Okay, so again, your book goes through an example of round-robin scheduling. And here we have process 1 is 24 milliseconds. Process 2 is 3. Process 3 is 3. And, you know, we can assume here that our quantum, our time slice is 4. So process 1 is the first process. It gets into memory, uses up its time slice, and it's out of there. The second process is given the CPU, gets its time slice of 4, but it's done after 3 milliseconds. So it's out of there, and process 3 goes into memory and is allocated the CPU. It may already be sitting in memory, but it's allocated the CPU. After process 3 ends, and again, it doesn't use its whole time slice, then process 1 is given each quantum after that until it finishes its work. Okay? So you could see if we were just doing first come, first served, process 2 would be waiting for 24 milliseconds, and process 3 would be waiting for 27 milliseconds because it'd have to wait for process 1 to be done and process 2. And so we'd have a fairly large average wait time. Here, because we do this time slicing with the round robin, process 1 didn't get to hog the CPU. Process 2 was given a chance, process 3 was given a chance, and then process 1 was given the CPU back. And so the average wait time was 5.66 milliseconds. All right? So again, the Q, and when I say Q, I mean the quantum here, should be large compared to the context switch time. And it should, you know, a context switch is usually like 10 microseconds, okay? So here our quantum is much larger than the context switch time. So we're in good shape here. So here, typically when you're using a round-robin scheduling, the average turnaround is a little bit higher than if you're doing shortest job first. But you usually get a better response time because these processes got into memory and were able to you know, do something where they can then go back and respond to the user. So again, we're talking about the different trade-offs that you're going to see. Excuse me, I need to take a drink of water. Okay, so let's continue on here. It's getting even more complicated when we start talking about a multi-level feedback queue. What this does is it looks at the ready queue and it actually divides it up by categorizing the processes and putting the different categories into different queues. So here's an example that your book gives of how things might be categorized. You may have system processes, and remember we talked about what they are. They may be categorized higher than interactive processes. Remember, interactive processes are those, you know, where there's a user waiting for a response, and they may be categorized higher with a higher priority than interactive editing processes. You know, somebody's sitting there in a text editor, so they're actually typing, which you type relatively slowly compared to how fast the CPU can process things. And then there might be batch processes, and these are, you know, they're not interactive. They're where you submit a job and then, you know, sometime later you come back and get it. You're not actually waiting for a response from the computer. You're just waiting for it to be done in the end. And then maybe the lowest priority, if this was a school, might be the student processes. Okay, and I actually, you know, worked for a school where we were working on a mainframe computer, and this was pretty much how we set things up. We didn't actually have any interactive processes back in those days with the mainframe computer, everything was on punch cards. I know I'm showing my age, but but we prioritized all the system processes and all the batch processes, which were the all the work the school had to do, the accounting and the payroll and all that. We prioritized them higher than our students who were learning to program, and they were submitting their jobs to the CPU and compiling and so forth. Okay, so basically with a multi-level queue, what you're doing is you're assigning queues based on some attribute of the process, what's important in this process and its scheduling. Then each queue can have its own scheduling algorithm. For example, the interactive processes might use round-robin scheduling, but the batch processes use first-come, first-serve, because those are the schedulers, the type of scheduling algorithms that make sense for that type of process. Okay? Now, this gets a little complicated, though, because then the queues need to be scheduled themselves. In other words, we have to know that the system processes are the highest priority, so anything in that queue gets scheduled before a student process, for example. Okay? But when there are no system processes to run, or they're waiting or whatever, well then what queue do we schedule next? Well, it would be the interactive process queue. So we start with system and then interactive and so forth. So we might have a fixed priority preemptive scheduling where if something enters one of these higher level queues, it preempts something in one of the lower level queues. Okay? Or we could also do some time slicing. Okay, and give each queue, a certain slice of time. Okay, so there's, it just keeps getting more and more complicated. And then to make it more complicated still, we have what is called multi-level feedback queue scheduling. And so with multi-level feedback queue scheduling, we not only have multi-level queues, but we can move processes from one queue to another. So when we do multi-level queuing, what we're doing is we're not just putting things in different queues depending on their characteristics and then scheduling the queues and then scheduling the processes within the queue. We're also moving processes. We can move them, to a higher priority queue or to a lower priority queue. They're not fixed. They don't stay in that queue. They can move around depending on what's happening in that process. When you're doing something like this, there's so many things that you need to decide on. How many queues do you have? What scheduling algorithm are you going to use for each queue? When do you upgrade a process and put it in a higher priority queue? When do you demote a process and put it in a low priority queue? And then what queue did you put a process in when it first enters the system? Okay, all these decisions have to be made, and you can configure your operating system a certain way, and then your algorithms that are written in the operating system are making these decisions. Okay? So your book also goes through a multi-level feedback queue example, and it shows, there's 3 queues. There's a round-robin queue with a quantum of 8 milliseconds. We have a round robin with a quantum of 16 milliseconds, and then we have a first come, first serve queue. So we have 3 queues. The scheduler will run all processes in Q0. When Q0 is empty, it'll run the processes in Q1. But if a process arrives in Q0, which is the higher priority, it's going to preempt whatever was going on from Q1 and go back to running the processes in Q0. Okay? So only when Q0 is empty will it run all the start running the processes in Q1, and then when Q1 is empty, it'll run all the processes in Q2. Okay, so it's going to give the first queue the highest priority, and that has the time quantums with the lowest amount of milliseconds. Then it'll run all the processes in Q1, and then it'll run all the processes in Q2. And when it's running a process in Q2, if anything comes into Q0 or Q1, it'll stop running the process in Q2 and go and run the higher priority process. So the other thing that happens here, though, is that new processes are going to be moving around in these queues. All right? So a process might originally start in Q0. So it might originally start here. If it's not completed in 8 milliseconds, which was the time slice, it might get bumped to the lower priority queue that has a larger time slice. Okay, so now when the CPU gets around to being allocated to Q1, that process now will have an additional 16 milliseconds to complete. If it doesn't complete in that 16 milliseconds, it might get moved down to Q2, which is a first come, first serve low priority queue. Okay? So you can see how it just keeps getting more and more complicated. Now you have another question in your homework assignment. Oh, let me skip this. And that is exercise 5.14. And this says, consider a preemptive priority scheduling algorithm based on dynamically changing priorities. Okay, so the priorities are going to be changing. It's preemptive priority scheduling, but the priorities are going to be changing. Larger priority numbers imply a higher priority, okay? And this changes from system to system, whether a large number means a high priority or a large number means a low priority. In this case, it's saying a large priority implies a higher priority. When a process is waiting for the CPU, it's in the ready queue but not running, its priority is changing at a rate of alpha. When it is running, its priority changes at a rate of beta. All processes are given a priority of 0 when they enter the ready queue. The parameters alpha and beta can be set to give many different scheduling algorithms. So the question is, when beta is greater than alpha and alpha is greater than 0, what scheduling algorithm will result? In other words, when it's running, if its priority is changing at a rate of beta and beta is greater than alpha, what's going to happen? Okay, the other question is, what is the algorithm that results from a alpha being less than beta and that being less than 0? And again, here, your answer is going to be something short, like RR or FCFS or SJF, you know, the scheduling algorithm. That's what I mean when I'm asking what algorithm results. What is the scheduling algorithm? But the important thing here is I want you to explain how you came up with that. Explain why you think it's a first come, first serve algorithm, or a shortest job first algorithm, or a round robin algorithm, or a priority algorithm, or whatever you think it is. Okay? So you have to kind of look at what's going to happen as the priority changes. You know, play around with, make your own little pictures of processes and how they come into the system, and what happens if beta is greater than alpha and they're both greater than 0. And what happens if alpha is less than beta and they're both less than 0. Okay? So I want you to take a look at that as well and explain why you think it's going to result in an algorithm that looks like shortest job first, or looks like a round robin algorithm, or looks like a first come first serve algorithm. Explain why you think that is. All right? We still have a little more scheduling to talk about, and I'm going to go through these next couple slides kind of quickly. It is all in your book, But remember when we talked about multiprocessors last week, we said there was, asymmetric multiprocessing and there was symmetric multiprocessing. And if you think about it, if you remember from the prior week, asymmetric multiprocessing meant that there was a single master processor that runs the operating system, and that's doing the scheduling, the I/O processing, and the other system activities, and the other processors run user code. Okay, I think we might have even talked about this in week 1, not week 2. So in this case, one processor is doing all the scheduling, and the other processors just run user code. Whatever user code is put in their queue, it runs it. It doesn't worry about the scheduling. Symmetric multiprocessing, on the other hand, each processor is self-scheduling. So what happens in an SMP system, symmetric multiprocessing system, is that you might have just one ready queue, and all the different processors are pulling things from that one ready queue and running them. Okay, so of course there's some issues there because they're sharing this ready queue, and you want to make sure that they don't, corrupt it and everything is getting taken care of in the right order. And then the other thing is that some systems actually have separate ready queues for each processor, each CPU. Okay, so there's different ways, and you can think about how this would complicate the algorithms if they're sharing, and also if they have separate ready queues. Can things move from processor to processor within a multiprocessing system? And then within that processor, what's the scheduling algorithm? And if it's a multi-level, multi-queue scheduling, what are the priorities? What are the rules? Can they move from level to level, from queue to queue? I mean, you can just see how complicated this gets as you're writing an operating system. Most modern operating systems do support SMP, the symmetric multiprocessing. And some of the things that, as you're doing scheduling between these different processors, some of the things you have to consider is processor affinity. A process usually performs better if it stays on the same CPU, if it's not moving between one CPU and another, because there's less stuff that has to happen when the process is allocated the CPU and then if it's preempted. Okay? On the other hand, you want to make sure that all the CPUs are doing the same amount of work. Okay? So you want to make sure that there's a balance, a load balancing happening between the CPUs. So there's a trade-off between processor affinity and load balancing. You want to keep the process on the same CPU if you can, but what if there's a couple others just sitting around doing nothing and one CPU has a whole bunch of stuff in its queue? Okay? So these are, again, more trade-offs that have to happen. Now, when you get something where one CPU is very busy and other CPUs are more idle, you have a couple different ways it could be handled. There's something called a push model, where the overloaded CPU gives its work to the idle ones in an attempt to balance the workload. Or there's the pull model, where CPUs that are idle, that aren't doing anything, will pull the work from the busy CPUs. Okay? So again, there's so much that's going on under the covers, and when you think about it, we don't have multiprocessors on our phones, but a lot of this stuff that we're talking about, all these different scheduling and whatever, this is all happening on our cell phone. Okay? So you can just kind of think of some of that. Then, to complicate things even more, we have thread scheduling. Remember, we've been talking about threads. But remember that threads are separate threads of execution within a process. Okay, and user threads, which is what we think of as threads because we're programmers who are, usually writing at using the user level threads and using the thread libraries. These are mapped to kernel level threads, and the kernel level threads are what get scheduled by the operating system. Okay, so we usually work with user level threads, but remember that they're mapped, and we saw pictures of that, the many-to-many, the many-to-one, and the one-to-one mapping between user level threads and kernel level threads, and it's the kernel level thread that gets scheduled by the operating system. Okay, so not only are we worried about processing or scheduling processes, we're also worried about how are these user threads mapped to kernel threads, and how are these kernel threads being scheduled on the CPU. Okay, so it just gets more and more complicated as it goes on. When we have this kind of situation where we have user threads being mapped to kernel threads, there's a couple things that can happen. In your one-to-one and many-to-many models, where you have many user threads being mapped to one kernel thread, or many user threads being mapped to many kernel threads, the thread library usually takes care of scheduling the user level threads. Okay, not actually scheduling it on the CPU, but scheduling it on the lightweight process. And this is known as process contention scope. Okay, in other words, the thread library is looking at the threads within a single process and saying which thread in this process should be scheduled. And then that thread, that user thread, is mapped to the kernel thread, which then gets scheduled onto the available CPU. And that's called system contention scope, where it's competition on all the threads in the system competing for the CPU. So there's kind of the different scoping. One is what thread within a job or within a process is getting scheduled, and then of all these threads that can be scheduled, which one actually gets the CPU, which kernel thread that it's mapped to gets the CPU. All right, so it's complicated. We also need to take into account real-time CPU scheduling. Okay, and your book goes through a lot of this and the things that have to be considered with real-time scheduling. Because with real-time, remember that you're waiting for an event to occur, and then what happens? Real-time is things like, the brake system in your car. When you tap the brakes, you want to make sure that that processor gets that event right away. Okay, you don't want it to be waiting for something else to happen. So there's different considerations when you're talking about a real-time system versus, the normal kind of system that we use. Okay, a lot of times these real-time systems, you're waiting for an event to occur, and the latency is the time from when the event occurs to when it gets serviced. And different events you're gonna want to have a different amount of latency. Like I said, when you hit the brakes on a car, or the person who's driving your car, when they hit the brakes, you want to make sure that gets priority. That event that happens, and because there are computers in your car, that gets processed as soon as possible. The latency isn't as important, let's say, when you're talking about an airplane and it's updating its radar. Okay, it doesn't have to be immediate. It could be a second or so before something appears on the radar, because it's not as critical as whether or not you're going to hit the car in front of you. Okay. So that's one of the considerations. And then, there's all these different scheduling things that you have to consider. There's priority-based scheduling, which we talked about priority and preemption and how, higher priority things should preempt the CPU, the allocation of the CPU. They should get the CPU next. We have monotonic rate scheduling, and this is where periodic tasks, things that they're going to be happening over and over and over, they get scheduled with a static priority, and then there's preemption that could happen here. There's earliest deadline first, and this is something where certain things have to happen first in the system. Okay, it's a real-time system. There are real deadlines that have to be met, and so an earliest deadline first scheduling would prioritize by deadline. And it's kind of how I prioritize things. I mean, whatever I have a deadline for, that's what I do first. Okay? And if something else comes up that has a sooner deadline than what I'm working on, I drop what I'm working on and I do that. So I get it done in time for the deadline. And that's how earliest deadline first scheduling works. Okay? Proportional share. This is where all the applications get a share of time on the system. And then the book also talks about POSIX real-time scheduling, and this is an API for real-time threads. Okay, and so again, with real-time, we have all these different kinds of scheduling algorithms. Things are going to be, first come, first serve. They're going to be round robin. There's priorities. There's preemption. And again, there's different considerations when you're working with a real-time system. Your book also goes into some examples of operating systems and what kind of scheduling they use. And I kind of summarized it here. Linux has preemptive priority scheduling, and it has priority classes. Remember, we talked about the categories when we talked about the scheduling. The priorities are divided into real-time and nice, and so they're given a priority depending on their class. Windows also has a preemptive priority scheduling. They have their classes divided into variable and real-time, and they're given a priority. And then priority 0 in a Windows system is the thread that does the memory management. And then Solaris has priority scheduling, and they have 6 different priority classes: time-sharing, interactive, real-time, a system priority, fair share priority, and fixed priority, because a Solaris system is a server where it may have many interactive users connected to it. And so it has different priority classes to handle that. And it uses a multi-feedback queue for its time-sharing system. Okay, so the interactive users will get their time slices and so forth. Okay, we also need to talk a little bit about evaluating scheduling algorithms. We've talked about these different algorithms. There's a lot more than what we've talked about here, different ways you can schedule things. Actually, my husband did his PhD research on scheduling and did a simulation of an operating system and used artificial intelligence to help make some of these decisions in an operating system. So there are all these different algorithms, and they have different strengths and weaknesses. And what we have to do is we have to quantify each algorithm in order to choose and make an informed choice. What's going to be good on our system? And it varies by system. How is the system going to be used? But the important thing here is, how do we actually, quantify it? And once we quantify it, then we could decide, well, is this what we need for our particular priorities. Remember I said, well, what's the most important? Is it throughput? Is it response time, and so forth? So we would have to evaluate them, come up with a quantity, and then compare them to see, well, is it minimizing this? Is it maximizing that? And does that match our needs for the system? So there are a number of different evaluation techniques that you could use. There's analytic evaluation, and that determines the performance of an algorithm for a certain workload. So it uses the algorithm and a specific workload to produce a formula or a number that's going to be used to evaluate the performance. Okay, so that's basically deterministic modeling. It's a type of analytic evaluation. You have a preset workload, a predetermined workload, and you look at what is the performance for that workload. What does the throughput look like? What does the wait time look like, and so forth for that workload? And then you would determine whether that's the algorithm you should be using for your system. You can also model, evaluate algorithms by using queuing models. And here with queuing models, queues are used to model the system resources with, and so it's like they're modeling the servers for those resources with queuing properties. So you look at the distribution of the CPU and the I/O bursts, and you look at the probability of whether or not a certain CPU burst is going to happen, and what is the arrival time for the CPU burst in this distribution, and you can actually plug it into a formula called Little's formula, where you can calculate the average throughput or utilization or wait time. So if you know the queue length and the arrival rate, and here we're talking averages, you could compute the average wait. Or if you know the wait and the queue length, you could compute the average arrival time. So if you have two of the things in Little's formula that you can come up with by doing these queuing models, you can use those two things to compute the third variable. Okay. So again, it's a little more complicated to do this, but you may end up with a more accurate analysis of your algorithm. To get even more accurate than that, people often do simulations, and here's where you write a program to model the system, and then you either process real or statistical data in order to simulate what's going on in the system. Okay, you might have logs from a system that's currently running, and then you might simulate a new scheduling algorithm and run those particular processes, or the numbers for them, how long it waited and so forth. Run that through. What its CPU burst look like, and use that to actually model what it will look like if you implement this new scheduling algorithm. And then finally, the most expensive, but probably the most accurate, is to actually write the scheduler and try it, see how it does. Okay? Not recommended, but sometimes it's the only way you can get the answer. Okay? So we have all this different kinds of scheduling, and scheduling is being done all over the place, and so far we've only talked about CPU scheduling. We're going to be talking about other things that are happening in the system, and things like allocating memory and scheduling I/O and that type of thing. And so we have all these different queues, and we have all these different schedulers and all these different scheduling algorithms. And as you're writing an operating system, you have to decide all this, and you do it by evaluating the different ones. And for that particular system, figure out what is going to be the best algorithm for you to use. What is the best scheduling algorithm for you to use? Okay. So that's all I had in these charts. Again, read through your book. Your book goes through a lot of this in detail. If you have any questions, please feel free to ask me, ask on the discussion board, or send me an email. And I'll be happy to help you out in any way I can. All right. See you next week. Bye-bye.